let's start to maybe put some things together here about the skill we've been looking at of adding up an infinite number of these values of whatever these expressions represent, and to start looking at the next big topic in calculus, which we started on with those area approximation models. And now we're going to sort of formalize that a bit and say, well, what if we want some exact area? And so there is some symbol notation you should be aware of that is going to kind of, we need to be able to read and say, hey, this is looking for area. And so that's this symbol right here. This is an integral symbol, and it'll have a lower bound and an upper bound. And that integral symbol means find the area under this particular function, under this particular curve. Okay, so this is what's called the definite integral. Okay, and this definite integral is basically a symbol that says find the area. Okay, so when you see this, it's saying find the area under the curve. So our interpretation is find area under the curve. And it's going to start at A, end at B. Start at A, end at B. Right? And like this right here, this function is what you'll be given. Or you'll be given its graph or something, but you'll be able to know what that function is. Now, suspiciously, there's this dx here, which we think of as like differentials or derivatives. And for now, that's just going to sort of be like a placeholder. It's not going to really mean anything just yet. But you should be suspicious of it because it has something to do with derivatives, what we're doing, which is going to be so weird because we're just calculating area. Okay, so here's what I'm going to do. It says, use the limit definition of an integral. Sorry, so there's an integral, right? To evaluate this. And so when you see integral, we're looking for area. And we want to find the area under this curve, starting at 1 and ending at 3. Well, the curve itself is linear. So like, I don't necessarily need to use an integral to find it, but it also makes for a good example of checking to make sure we're doing this right. So from 1 to 3, if I were to graph 2x plus 3, so if I put in 1, it would have a height of 5. And if I put in 3 is the other boundary, that's 6 plus 3 is 9, I have a height of 9. So here's the curve. So it's linear. I could easily find this area. But instead of finding the exact area, I'm going to use one of our approximation models. I'm going to use an RAM, and a lot of things will be defined by the right side here. I could have picked left, I could have picked middle, but we'll stick with R, the right side. Okay, so rather than finding the exact area, I'm going to find an approximate area. So I'm going to pretend I'm creating some rectangles here, and I'm just going to use the right side of the rectangle, and I want to make them all the same width. So whatever that width is, obviously it depends on how many rectangles I have, right? So I have these rectangles here, and I know how to find the area of a rectangle. The area of a rectangle is just base times height. Area of a rectangle is base times height. And if I could find the area of this rectangle, and then this rectangle, and then this rectangle, I could just add them all up, right? So my area could be the area of this under this curve could be approximated by like whatever the first rectangle's base is times its height. So base 1 times height 1, and then plus the next rectangle, base 2 times height 2, plus the next rectangle, base 3, height 3, plus the next rectangle, base 4, height 4, and we'll just keep going until we get to the very last rectangle, which would be base whatever that value is. And since we've been using I to count the index of how many things we're adding up, it makes sense. It's called b sub I, and whatever the height is at that last interval. Now, if I want all these rectangles to be the same width, so right now I'm taking this whole distance from 3 to 1. So I'm taking 3 to 1, and I'm dividing it equally by however many rectangles I have. So let's say I have n of them. So that means every base of my rectangle could be represented by 2 over n. And again, how did I get that? Well, I looked at, well, this whole distance here from 3 to 1 is 2. Now divide it into n equal increments. So this base could be written as 2 over n times the first height. And then this base could be written as 2 over n times the second height. And this base right here could be written as 2 over n times the third height. And so we just keep going until we get the very last base, which is still 2 over n. And then it's whatever that last height is. Right? H sub I. Okay. So that's our area. Now, if we can somehow get an infinite number of rectangles, so think about that. Like if we let if we try to get an infinite number of rectangles, right? So let n go to infinity. That means obviously we're having an infinite number of rectangles, but it also means that the base of each rectangle gets smaller and smaller and smaller until basically those, pun intended, basically until those rectangles are no more than rectangles. But if your base is 0, they're just a bunch of segments, right? We're just adding up a bunch of segments, their area. And if we can do that, we would get the exact area under the curve. So that's sort of what our goal is. Now, let's figure out what these heights are, right? Let's look at this first height here. What is happening? So if you have your rectangle here, I'll undo that, undo this, go back to this green, okay? So when you have your, sorry, my bad. There you go. Okay. So we have that first rectangle. Let's look at that. Go into maybe blue. This first rectangle right here. Okay. So the height that we're choosing is on the right side of that rectangle. So we started so what is that point? Well, it's whatever the distance that interval is away from 1. So it's 1 starting at 1, and you're just 2 over n, wherever the increment is, away from that starting point. We take that value, we put it in the function, we see how high it is. So if I call this function, or this like our f of x, I can get that the base is still 2 over n. The height is whatever f of 1 plus that first increment is, right? Because I'm starting at 1. Because if it were left ram, then it'd be the left side would just be f of 1. This is now f of whatever the right side is. I'm 1 plus whatever that increment is. And then the next rectangle has a base of 2 over n. And then the height would be f of 1 plus 2 of those increments. And then the next rectangles would be the base, 2 over n, times f of 1 plus 3 of those increments, right? And we just keep going and going and going until we get to the very last one. And that very last one would be, again, the base of still 2 over n times f of 1 plus, if we have I of them, I of those increments. Now, I'm adding up a bunch of rectangles, and so this repeated addition makes sense to use a sigma. So let's think about this. Like we're adding up a whole bunch. So starting at I equals 1 to n of each of these elements has a 2 over n, and that's times f of 1 plus a certain number of those increments, I, right, times 2 over n. So, I mean, this is such a clean way to express this, right? Every one of these elements has a 2 over n, 2 over n, 2 over n, 2 over n. So put it there. Every one of these elements, it starts at 1, right? Starting at 1. So we start at 1. Every one of these elements is adding there's the first increment of 2 over n. There's the second increment of 2 over n. Here's the third increment of 2 over n. Here's the ith increment of 2 over n. So each of these base times heights can be represented by this. And what was our function? Oh yeah, our function was up here, 2x plus 3. So if I have function notation, I'm just going to put that into the 2x plus 3. So, oops, spoiler alert, there's our answer down here. Sorry, I thought I had erased it all. Okay, there we go. So don't look down there. Pretend you don't see that. There we go. So let's go ahead and put that into our function. So now we have, oops, my bad. Now we have summation I equals 1 to n of 2 over n, and then our function was 2x plus 3, so it's 2 times 1 plus I times 2 over n plus 3. Right? There's our 2x plus 3 function where we're inputting this value here. That's my x. So here's my x. So there's the structure, 2x plus 3. Okay, now we can certainly simplify this to get, so we have the sigma notation, I equals 1 to n. We have 2 over n, and then we have 2 plus 4i over n, 2 plus 4i over n plus 3. And again, I'm just distributing that 2 times 1 is 2, 2 times 2 is 4, 4i over n plus 3, and we can combine that to 5. So we have, oh, spoiler, don't look at that answer. So we have I equals 1 to n of 2 over n. We have 5 plus 4i over n. And if we want to distribute that 2 over n into this, I equals 1 to n, we could, so that's 10 over n plus 8i over n squared. So we know how to simplify this. We know that n is just a constant and that I is our counter. So we can actually think about, okay, so we have 10 over n, or basically like we could factor out the 1 over n. So we have 1 over n sigma I equals 1 to n of just a 10 plus, and then we can factor out the 8 over n squared, and it's sigma I equals 1 to n of I. And again, counting up tens, so that's 1 over n times 10n plus 8 over n squared times n plus 1 all over 2. Or that's 10n over n plus 8 times n plus 1 all over 2n squared. I know those cancel, right? So then I get 10 plus, and that could be like 4 n times n plus 1 over n squared. But remember, n represented how many rectangles, and how many do we want? An infinite number of them. So we let n go to infinity. And that doesn't affect this 10 at all. It's still 10. And if I think about this is going to behave like a 4n squared over n squared, which is going to behave like a 4. So we're going to get 14. And this whole model represented area because it all represented just adding up rectangles, right? And rectangles are just base times height. So if I do that, if I think about that, and I know then I got this answer of 14, then I want to just check my work. Is it really 14? So go back. This distance here was 2. We said, right, from 1 to 3. If you put in 1 into this function, 2 times 1 is 2 plus 3, this is 5. We said this was 9. So you have a trapezoid with a base of 5, remember it's vertical, a base of 9, and a height, which is base to base of 2. Area of a trapezoid is 1/2 2 times 5 plus 9, which is equal to 14. So that's the exact area. Now, it's a very long about way to represent that area, but the whole point of doing it in something that we know so we check our work is that what if you can't? What if your function is something like this? Oh, a quadratic, right? A quadratic doesn't have a formula like 1/2 base times height. So this approximation method, and then letting n go to infinity, so you have an infinite number of rectangles, is a really, really smart thing to do because it'll allow us to find that exact area. Okay, now I promise you, not every example is going to take this much time, but we're just learning this. So yeah, of course it's going to have to take some time, right? Okay, rewatch this, see if it makes sense, and then we'll just have to ask questions.